Hello everyone. Today I'm going to explain the Dining Philosophers Problem, which is a classic example in operating systems. It helps us understand how concurrent processes share resources and why issues like deadlock and starvation occur. I'll take you through the concept, the core problem, and some common solutions. Okay, so in this problem, we imagine five philosophers sitting around a round table. Each philosopher has one plate and alternates between two activities, thinking and eating. To eat, a philosopher needs two forks, one from the left and one from the right. But the important point is that the forks are shared between neighbors. This creates a situation where resource sharing decisions can lead to conflicts. Before understanding the problem deeply, we need a few basic ideas. Each philosopher represents a process or a thread. Forks represent shared resources. Eating represents entering the critical section. Now here, if two philosophers try to pick the same fork at the same time, we get a race condition. Mutual exclusion is required so that only one philosopher accesses a fork at a time. These concepts make it easier to understand what goes wrong. Now we move on to discuss the core problem. The main issue arises when all philosophers follow the same strategy. For example, if every philosopher picks up their left fork first, they all end up waiting for the right fork. This results in deadlock, where no one can continue. There's also the risk of starvation, where one philosopher keeps getting skipped and never gets both the forks. So the problem demonstrates how resource allocation can easily fail without proper control. Now, we'll discuss what is deadlock. Deadlock occurs when there is a circular wait, which means each philosopher is holding one fork and waiting for another fork that someone else is holding. Since everyone is waiting and nobody releases their fork, the system becomes stuck. This is exactly what happens in many computer systems when processes hold resources and wait for the other. Now, we'll discuss the solutions. To avoid these issues, several solutions are proposed. One solution is resource ordering, where philosophers always pick up forks in a fixed order, breaking the circular way. Another solution is limiting the number of philosophers who are allowed to eat at a time. For example, using a semaphore value of 4. The most practical solution is the waiter or butler method, where a central controller grants permission only when the both forks are available. Each of these strategies prevents deadlock in different ways. Now, we'll move on to discuss some real-world uses. This problem is not just theoretical. It models real issues in operating systems such as process synchronization and database locking. It also appears in multi-threading, where threads compete for shared data, and in network systems where bandwidth is limited. So the concept is very useful in real-world computing. To conclude, the Dining Philosophers Problem helps us understand how resource sharing can lead to deadlock and starvation. By studying this problem, we learn how to design safer, more efficient synchronization strategies in operating systems and multi-threaded programs. Thank you.